Hi everyone. Good morning, good evening, I guess. So should I get started off? I
No,
guess it's
Avril, I was just waiting for your presence. I was about to give you a call. So I
oh
thought
okay.
once you give me the green signal that yes, you have come, you have joined, then I will
Sure.
start a little bit of introductory session and then I will hand over the session to you and you can continue from there itself.
Sure.
Okay?
Okay. Sounds great.
Okay.
Yeah.
So thank you very much, Obrunil. Dr. Obrunil Sengupta has joined from USA, and as you know that there is a time difference of nearly around 11 hours. So it must be very early in the morning at USA, Obrunil.
Yeah, this is 9 a.m. now here. Yeah.
Now, very excellent. This is 9 o'clock in the morning, and I hope you had a good breakfast before joining this session. Okay.
Sure. Yes.
Okay, fine. Thank you very much, Abdunil. My dear friends, we are going to start the session right now. It is already, we are late by 2, 3 minutes, but that doesn't matter. We have with us today Dr. Abronil Sengupta from Penn State University, USA. I will just start the session with a very brief introduction and then I will read out the profile of Dr. Sengupta and then I will hand over the session to Dr. Sengupta to continue further.
Hello.
Please keep your set in mute form. Please, okay? Don't interrupt in between, okay? So we are going to start the session right now. So that's the topic for today's discussion is neuromorphic computing, bridging the gap between neuroelectronics, neuroscience, and machine learning. I will just read out a brief about this particular topic. While research in designing brain-inspired algorithms have attained a stage where such artificial intelligence platforms are being able to outperform humans at several cognitive tasks, an often unnoticed cost is the huge computational expenses required for running these algorithms in hardware. Bridging the computational efficiency gap necessitates the explorations of devices, circuits, and algorithms that provide a better match to the computational primitives of biological processings, neurons, and synapses, and which require a significant rethinking of the traditional von Neumann based computing. The talk will discuss innovations in emerging post-CMOS technologies that are revealing immense possibilities of implementing a plethora of neural and synaptic functionalities by single device structures that can be operated at very low terminal voltages. The presentation will also discuss recent innovations at the algorithm front on exploring event-driven spiking neural networks for large-scale machine learning tasks. Such neuromorphic systems can potentially provide significantly lower computational overhead in contrast to standard deep learning platforms, especially in sparse, event-driven application domains with temporal information processing. Dr. Sengupta will conclude the presentation by providing the prospects of enabling end-to-end cognitive intelligence across the computing stack that combines knowledge from devices and circuits to machine learning and computational neuroscience. Ladies and gentlemen, just for your information, this is a very upcoming field, and for the first time, Computer Society of India is organizing this kind of webinar in the country. We have not organized any such webinar till date, and I'm very happy to share with you that CSI Kolkata chapter, being a pioneer institute in the country, they are the first one to come up with this topic. And at the same time, I must also tell you that we have with us Dr. Sengupta, who is absolutely I should say a person absolutely from the scratch who knows the subject from scratch basically, and he is running a neuromorphic lab in Penn State University. As you know that Penn State University is a Ivy League University, the first 10 universities in US. And I'm extremely happy to share with you that we have with us Dr. Abronil Sengupta today with us. As you all know, that Dr. Sengupta is a professor in the School of Electrical Engineering and Computer Science at Penn State University. He is also affiliated with the Department of Material Science and Engineering and the Materials Research Institute. Dr. Sengupta received the PhD degree in Electrical and Computer Engineering from Purdue University in 2018 and B degree from Jadavpur University in 2013. He worked as a dad. All of you must be knowing German Academic Exchange Service Program. It is a fellow program at the University of Hamburg, Germany in 2012 and as a graduate research intern at Circuit Research Labs Intel Labs in 2016 and Facebook Reality Labs in 2017. Dr. Sengupta has published over 60 articles in referred journals. When I say referred journals, you must be knowing these are mainly the IEEE journals and conferences and holds 4 granted or pending US patents. He serves on the IEEE Circuits and Systems Society Technical Committee on Neural Systems and Applications, editorial board of Neuromorphic Computing and Engineering, Frontiers in Neuroscience Journals, and technical program committee of several international conferences like DAC, ICCAD, ISQED, GLS, VLSI, and VLSID. He has been awarded the IEEE Circuits and Systems Society, popularly known as CAS, Outstanding Young Author Award in 2019, IEEE SIPS Best Paper Award in 2018, Schemit Science Fellows Award nominees 2017, Bellsland Dissertation Fellowship 2017, CES PIN Student Presenter Award 2015, Brick Fellowship Award 2013, and Dadwise Fellowship 2012. His work on neuromorphic computing has been highlighted in media by MIT Technology Review, US Department of Defense, American Institute of Physics, among others. Dr. Sengupta is a member of the IEEE Electron Devices Society and Circuits and Systems, popularly known as EDS and CAS Society, the Association for Computing Machinery, that is ACM, and the American Physical Society, popularly known as APS. This is in brief about Dr. Sengupta, but those who are interested to know more about the subject, I would strongly recommend them that you please click on the neuromorphic labs which is being run by Dr. Sengupta at Penn State University, and I'm sure all of you will learn many new things which we normally don't know. So my request to you, just log into the website and just go inside the neuromorphic lab, which is maintained by Dr. Sengupta himself, and I'm sure you can enrich your knowledge. My dear friend, Dr. Sengupta is a very, very busy person, and as you know, he travels across US and other countries. And at this point of time, he is having number of official duties to perform. But in spite of his busy schedule, I have requested him to give a talk, and he has agreed. And without wasting any further time, I would now hand over the session to Dr. Sengupta. Dr. Sengupta, please.
Many thanks for the kind introduction, and I'm delighted to offer this presentation. So I was pre-informed kind of that there will be a lot of people. So what I have done is I have recorded the presentation just to avoid any internet glitches. So I'll play that, and if you guys see any problems on the other end, please keep me posted in the chat. I will be available after the presentation to answer any questions any of you have. So with that, let me try to share my screen. Hi everyone, welcome to this online tutorial of neuromorphic computing opportunities and challenges. I'm Abronil Sengupta, I'm an assistant professor
in the School of EECS at the Pennsylvania State University, and today I will be talking about various aspects of neuromorphic computing and how a multidisciplinary perspective across the computing stack, all the way from sensors to devices, circuit systems, and algorithms, is trying to bridge the gap between nanoelectronics, neuroscience, and machine learning to solve some of the key challenges that AI faces today. While some of the content in the tutorial will be probably biased towards some of our lab's own work, yet hopefully by the end of the presentation, I will be able to convey some of the interesting opportunities that neuromorphic computing has and the challenges it faces today. So over the past few years, deep learning has made significant strides in a plethora of fields. One example is shown on the left, where the Google DeepMind beat a professional human champion in a 19 cross 19 Go board game. Now, while this is an amazing feat, an often underestimated cost is the amount of computational resources and energy consumption that these deep learning systems end up taking. Although this is not a one-to-one comparison, a few years back, IBM tried to simulate the brain activity of a cat. And in doing so, it ended up consuming around a few megawatts of power just to simulate 5 seconds of brain activity at 80 times slower firing rates. And therefore, if we were to scale this number up to simulate the brain activity of a human being in real time, on the best possible supercomputer that we have today, the power consumption would be even higher. However, in stark contrast, the human brain does concurrently many of these cognitive tasks together. However, it only requires a few tens of watts to operate. And driven by this motivation, the field of neuromorphic computing is really trying to imbibe various facets of how learning, cognition, how the architecture of the brain is organized in the way we are designing our recognition algorithms, our underlying hardware substrate, and so on. So that's really the key motivation behind the field of neuromorphic computing, to mimic biology in order to leverage some of its efficiency. Before I go into technical details of my talk, I would just like to quickly discuss the basic terminologies I will be using in my presentation. What I have tried to do in this slide is categorize neural networks into various computing generations. So long time back, people started off with perceptron networks, where you have a set of incoming inputs I1 to IN coming into my basic functional unit, which is shown here. And really, this basic functional unit has somewhat remained unchanged for us as the generation of neural networks have progressed. What has really changed is the biofidelity level at which we are modeling the neuron and synapse functionalities, which are the key computational units inside this basic building block. So the synapses are really important weights of various inputs, which are scaled by the corresponding synaptic weights, and this weighted summation of inputs goes into my neurons for processing. Note that the key computational kernel over here that we are performing is a dot product, which will become important later on. And it is by learning of these synaptic weights that we end up building various types of recognition systems. Now, the neuron is basically a computing unit, and people really started off with very simple-minded abstractions of neurons, and the first generation of neural networks consider a step function where if your weighted summation of inputs is greater than a particular threshold, it generates a high value. If it is less, it generates a low value, and so on. Now, people were not able to really scale up perceptrons to large scale tasks, mainly because of the limited information encoding in the neurons, and therefore things quickly transitioned to the second generation of neural networks, which I am terming as the analog neural networks, in the sense that the neuron transfer function was now abstracted to be an analog function of the neuron input, like the one shown here. And this is currently the de facto standard that we have in deep learning today. And people were able to arrange these neural networks in deep convolutional architectures. Even today, you can have really 50 to 100 layer deep networks and so on. Now, in neuromorphic computing, we attempt to abstract the functionality of the neuron and synapse to a much higher degree of detail. These are referred to as spiking neural networks or the third generation of neural networks. And let me try to first explain the basic underlying principle of the distinction between a spiking neural network and an analog neural network, and then I will try to outline the main reason why you would like to transition to spiking neural networks. So first of all, spiking neural networks operate as a function of time. So it is a time step based or a time domain based evolution of neuron function. And the neuron really computes when triggered by binary spike based information, which is 0 or a 1. So this slide shows an incoming input spike train, and you are seeing here the membrane potential of the neuron, which is an internal state variable of the neuron, which integrates incoming spike data and leaks whenever you do not have a spike. It keeps on integrating the incoming spikes and only generates an outgoing spike whenever the membrane potential crosses a particular threshold, and then it gets reset to some baseline ground value. Now, given this mechanism of computation, first of all, therefore, the neuron computes only when triggered by incoming spike-based information from the previous layer, right? So there's this advantage of compute only when needed. You're not computing all the time. You're computing only when you're being triggered by a high spike value from the previous layer of neurons. And if this spike train is sufficiently sparse, then you end up getting a huge amount of power savings when you are trying to implement in a hardware framework that can leverage this event driven computation as well as data communication. So because of this binary nature of data communication as well, the interconnect overhead is also much less. So power consumption wise, if I have enough sparsity in my spike train, I am able to significantly reduce the power consumption of my chip due to this event triggered behavior of computation and communication. And by leveraging that, there has been multiple works from IBM. Intel very recently has come out with the Loihi chip, where they have been able to leverage this event driven computing framework to demonstrate significant power savings. Another advantage of spiking networks is an unsupervised mechanism of local learning that is observed in synapses, and there have been works to leverage such kind of plasticity mechanisms for unsupervised local learning. I will go into details about the learning in a later half of the presentation. Now, given that at the algorithm level, we are interested in spiking networks from the advantages of event-driven computation, let us try to also understand what the inefficiencies are in current CMOS-based implementations of spiking networks. So, the key point that I would like to mention here is that all the circuits that we are designing using CMOS, the fundamental circuit blocks are really CMOS switches, which are on-off switches essentially, and therefore they are more suited for Boolean logic kind of implementations and may not necessarily map to the computational primitives of neuron and synapse. For instance, if I am trying to implement the dot product of the neuron, I will end up requiring a large number of multiplier and accumulator units, right, which is significantly area and power expensive. If I were to think of a synapse, which is kind of a memory element, I need to store the synaptic weights. For each bit of the synapse, I'm really looking at 60 or an 80 SRAM cells. So I'm really, for a 4-bit synapse, I'm ending up consuming around 24 to 32 CMOS transistors. So there is not a direct one-to-one mapping between my hardware building blocks and my algorithm building blocks. So therefore, this is one of the disadvantages that we have currently in CMOS-based implementations of spiking networks. Now, interestingly enough, recent experiments in various emerging technologies, I am showing spintronics in this slide. However, there are other technologies like resistive RAMs, phase change memories, ferroelectric devices, and ferromagnetic devices, for instance, the one that is shown over here, where it has been possible by leveraging some of the intrinsic physics, it has been possible to mimic various neuron and synapse functionalities at a one-to-one level in singular device structures which can be operated at very low terminal voltages. For instance, I'm showing a magnetic tunnel junction stack over here, which has been triggered by a set of incoming current pulses. And as you see over here, the conductance of the device integrates whenever I pass an incoming current pulse and leaks if I am not applying a pulse. This behavior mimics very closely the leaky integrate fire spiking neuron characteristics that I'm showing on the left. And even if you were to sit down and really understand the underlying physical evolution of the magnetization inside the device, which is dictated by something which is called the LLGS equation or Landau-Lifshitz-Gilbert-Slonczewski equation, you will find that there are resemblances of the equation with how the leaky integrate fire spiking neuron equation looks like. And there are not only, like this discussion is not only limited for magnetic tunnel junction devices. For my talk today, I will be using spintronic devices as an example hardware platform to explain various concepts. But there are, as I mentioned, many of these technologies. It is not clear today which one will be the winner in the long run.
Hello,
Each
sir.
technology has its own advantages and disadvantages, and there is no ideal material system today where we can say that, okay, this is the best one at the moment. Everything has its own advantages and disadvantages, which I'll try to also go into a bit later into the discussion. So this is more from a functional unit perspective. Now, one other disadvantage that we have in current CMOS implementations is something which is referred to as the von Neumann bottleneck. Current architectures usually store the synaptic weights in a memory, and then you have the processing core which repeatedly fetches the synaptic weights from the memory, processes it, and writes back to the memory. And because neural network models are very memory intensive, right? These models consume a lot of memory space. There is significant amount of energy consumption involved in these memory transactions. This shows a simple-minded analysis from one of our past works where we tried to determine the energy distribution as a function of increasing complexity of data sets for recognition purpose from the left to the right. So as we go for more complex data sets, we really need much more bulky neural network architectures in terms of memory, and therefore, as you can see, the total proportion of memory the total proportion of memory access and memory leakage energy that is there as a function of the total system level energy consumption can be greater than 50%. And therefore, this contributes hugely to the energy consumption of the entire system. Now, recent experiments, as I mentioned, in these spintronic devices or other technologies have revealed the opportunity to design non-volatile memory elements where you can program the state of these devices to arbitrary resistance states. And by arranging these devices in a crossbar array kind of fashion, by simple application of Kirchhoff's law and Ohm's law, I am able to implement the dot product kernel in these memory arrays. And if you remember, dot product was really one of the key computing kernels that we needed in the neural network. So this is a very nice fit with the kind of computing that we require. And I can briefly explain how this is implementing the dot product. So assume that each of these devices has been programmed to a particular conductance state. Let's say GI. If I apply a voltage along the row, the current that will flow through this synaptic conductance will be the voltage times the conductance value. And all these currents from Kirchhoff's law will get summed up along the columns. And therefore, what I end up getting along the columns is the weighted summation of the voltage inputs. So these are first of all non-volatile memory elements, and therefore I'm embedding the dot product computing kernel inherently in the memory array. So these in-memory computing kernels are alleviating some of the energy bottlenecks that we face today due to the von Neumann nature of computing observed in CMOS systems. First, let me talk about neuromorphic algorithms. Now, because spiking neural networks are a significant shift from standard deep learning networks that we have currently, because of its temporal event-driven nature of computing, scaling the recognition accuracies of spiking neural network architectures in large-scale machine learning tasks has been a challenge. And although over the past couple of years we have been able to significantly bridge that gap in accuracies, and the hope is that in the future, as we are investing research efforts to really leverage some of the untapped potentials of spiking networks in terms of sparsity, event-driven computing, temporal information processing, we would be able to hopefully outperform standard deep networks today, or have inherent application domains that are very much catered for spiking neural networks because of its unique properties. Now, in terms of training methods for spiking networks, some of the early works have really focused on spike timing dependent plasticity learning, which is an unsupervised mechanism of local learning that is present in biological synapses. And it is kind of an unsupervised clustering mechanism. Now, the key advantage is local learning, unsupervised learning, although the accuracy is not as great as you would get from supervised training, but that is kind of expected since we are not really utilizing any labeled data. Such unsupervised clustering mechanisms are very much attractive for enabling on-chip learning in edge devices where anyways we do not expect labeled data in real time. I will go into details about STDP learning a bit later in the slides. The other approach is supervised training, and you can do a backpropagation through time to train the spiking network. Some of the scalability challenges there stem from the fact that, first of all, that backpropagation has to be done through time. Second, because of this discontinuous reset operation every time the neuron spikes, people have had to use surrogate gradient methods to really approximate the gradient of the transfer function of the neuron for backpropagation to take place. So while backpropagation training of SNNs through scratch is definitely possible and is an active research field currently, as an intermediate step, many researchers have been looking at leveraging some of the training techniques for standard deep networks and converting that to a spiking network for the advantages of low power event-driven inference. I will mainly focus on this because our lab has been working in that domain for a while. And in terms of the underpinnings of AN and SNN conversion, the main reason why you're able to train a standard deep network and convert it to a spiking model is because if I were to consider, let's say, a rectified linear transfer function, then the basic functionality is that for negative side of inputs, I expect a zero output, and for positive side, I expect an output which is directly proportional to my input. The same mechanism also happens in a spiking neuron over a period of time. So if I were to receive negative spikes or negative incoming information from the previous layer, I would never be able to cross my threshold. So no spikes would be observed. However, if I am in the positive spike domain, and more the rate of input spikes I get, more will be the rate of output spikes. So therefore, that proportionality kind of comes across from that factor. And therefore, if I were to train a network with ReLU transfer function, I can convert that to an integrate fire spiking neuron with very minimal drop in the recognition accuracies. And we have been able to show really state-of-the-art accuracies for VGG ResNet kind of architectures on CIFAR 10, CIFAR 100 or ImageNet dataset, which is kind of state-of-the-art in the field. As you see, the advantage really stems from the sparsity of spiking of the neurons, and because of these computing only when needed scenario, you have significant power benefits in a spiking network. Recently, we have been looking at very simple-minded design optimizations, how I am designing the neural nodes, how I am resetting the neuron, what architectures are we looking at in terms of pooling operations, etc. Because when you're doing the conversion, you have to remain very much mindful of several constraints so that you minimize the accuracy loss during the conversion process. I'm not going into too much details on those design options at this point, but I would encourage all of you to take a look at one of our recent papers. Now, going forward, we also wanted to understand interplays of spiking neural networks with another hot topic in the neural network community, which is binary neural networks. So, driven by the power consumption concerns that we have in current deep networks, people have also tried to reduce the precision of standard deep learning networks to the extreme quantization regime of binary bits. And there has been a plethora of work over the past few years in the hardware community on exploring hardware accelerators catered for binary networks, simply because of the fact that reading out from such a in-memory computing array is very easy. You only need to program two states in these memristive devices. These are the memristive devices interfaced with an access transistor, and each of these devices are really in the high resistance or the low resistance state. So there has been a lot of work in the community on really hardware primitives, in-memory computing primitives catered for binary neural networks. But where does spiking networks stand in that picture? Spiking networks are networks where the neurons are abstracted as 0 or 1 over time. The weights were still full precision, right? So what is there any link to this ongoing research in binary neural networks, and how does spiking neural networks then compare against binary neural networks? So in one of our recent works, we tried to explore that domain. And what we really found out was that an interesting property that, and this was really guided by a recent study that showed that binary neural networks are really providing low accuracies when scaled to large scale machine learning tasks. And it was found that it was really the bit discretization in the neurons that mattered, and the synapses could be reduced to binary precision, but the neuron discretization to single bit was what was causing the major problem. So driven by that observation, we really tried to explore whether we could have spiking neural networks with binary quantization in the synaptic weights. And we found out that binary spiking neural networks actually exhibited near full precision model accuracies. And that's a really cool thing, because now I can implement these binary spiking neural networks in the core compute primitive, the hardware backbone of in-memory computing catered for binary neural networks, and just operate it over time to get to near full precision accuracies, which is a significant advantage therefore. So no accuracy degradation, I'm still operating in the binary regime because now I have binary synaptic weights, binary neurons, but just because of the temporal information integration of the spiking neurons, I'm able to retain the accuracy of the full precision model. This slide summarizes our recent results using ANN-SNN conversion. As you see, the left-hand table summarizes the results for CIFAR 100. If you observe, the full precision accuracy is around 64.9%. The XNOR net, which is the binary version of this full precision model, exhibits an accuracy of 47%, which is significantly lower. Our binary spiking neural network is very close to this full precision accuracy. Even if I observe our model trained on the ImageNet, full precision SNN gives us around 66.5. The binary version gives us around 62.71. And this is in comparison to actually previous works on ANN-SNN conversion. I remember I told you that we were exploring different design time and runtime optimizations for the ANN-SNN conversion scheme. So as you see, the accuracies and the number of time steps both are significantly lower. Like the accuracy is definitely higher for us. The time steps is significantly lower than the ANN-SNN conversion, as well as for a hybrid training scenario. So some of the recent works have also shown that if I were to train a network initially by ANN-SNN conversion and fine tune then on after that using backpropagation through time, it is possible to significantly reduce the latency. What we show is that by simple modification of the conversion scheme and the constraints, you are able to get to almost ANN accuracies in less than 100 time steps. So while, and I would encourage all of you to check out this publication, and we have made all the codes available in open source in GitHub. So while these results really give us proof of concept that spiking neural networks indeed can be scaled up to large scale machine learning tasks with accuracies that are comparable to what deep learning gives us today. And really, the conversion scheme, I believe, is kind of an intermediate step. And as we are utilizing more computing resources and we are able to train these spiking networks directly from scratch using backpropagation through time, they have a huge amount of potential of giving us interesting features in tasks that really involve temporal information processing. Many of the tasks that we currently are benchmarking on are really still static image recognition tasks. And as we transition to temporal domain tasks, like for instance, works that try to interpret event sensor data, where you have some temporal information content, there we would be able to hopefully leverage some of the unique properties of spiking networks and really do a training through time to get interesting results. Next, I will be discussing some of our works on the hardware side on all-spin neural networks using ferromagnetic devices. The basic device structure that we are going to use is that of the magnetic tunnel junction, where you have two ferromagnetic layers separated by a spacer layer. One of the layers, that is the free layer, has the magnetic orientation which can be manipulated in either of the two stable states, the up state or the down state. And the other layer is a pinned layer which is fixed in one particular direction, and depending on the relative orientation of the free layer and pinned layer, I can have two stable resistance states, the parallel state and the anti-parallel state in the magnet. We can switch between these two states by either an external magnetic field or by an input spin current. So for instance, if the current flows from the left to the right hand side, I can switch from the parallel to the anti-parallel state and vice versa. Now, in order to implement any neuromorphic functionality, as I mentioned, I really need to play with multiple internal states, right? That's the key functionality we are looking for. Otherwise, things would have been fine with CMOS Boolean switches, right? So two states is not sufficient. And therefore, in order to implement multiple resistive states in the magnetic tunnel junction, we use a ferromagnetic free layer which has an extended dimension in the lateral side to stabilize multiple magnetic domains in the free layer. And by passing a charge current between the right and ground terminals depending on the magnitude, I am able to program multiple domain wall position states in the free layer, which ends up modulating the relative proportion of parallel and anti-parallel domains in the MTJ and therefore the MTJ conductance. This structure is referred to as the domain wall MTJ, which I am showing over here. One additional effect that we use for energy efficient write is that of spin orbit torque introduced by a heavy metal layer lying at the bottom of the ferromagnetic layer. Because of spin orbit coupling, every incoming electron flowing through this heavy metal layer will get scattered at the ferromagnet heavy metal interface and therefore transfer multiple amounts of, or multiple units rather, of spin angular momentum to the ferromagnet lying on top. So it's a much more energy efficient write mechanism than spin transfer torque. And the device structure has three terminals, T1, T2 and T3. Depending on the magnitude and direction of current flowing through terminals T2 and T3, I will end up programming this domain wall location, the white spot on the ferromagnetic strip, and this will end up modulating the conductance that I read between T1 and T3. So the advantage of these three terminal device structures is of course the decoupled write and read current path. And also one important point to note here is that the write current flows through a very low resistance heavy metal and does not go through the tunneling junction barrier, which will become important as we move over from the device level towards system level demonstration. These represent the parameters we benchmarked our device model to cobalt, iron, platinum strips, and as you can see, representative energy consumption and power consumption numbers are mentioned over here. And one of the key takeaways I would like to point out over here that these domain wall MTJs can be operated at very low switching energies. And these are really magnetometallic devices which require very low currents for switching. And while at a standalone device level, this is of course an important efficiency metric, these will become very important as we go towards device circuit and system core design. These will be important properties that we will try to leverage. Now the previous device structure that I mentioned is of course can be used as a synapse. Depending on the particular location of the domain wall, I can essentially think of my MTJ to be a parallel combination of the parallel and anti-parallel domains, and depending on the domain wall location, I can program multiple resistive states in my device. So that behaves as a synapse. The same device structure can also be used as a neuron by simple modification of how we are designing the circuit. So this is the same device structure that I showed for the synapse, except that it is now interfaced with a reference MTJ at the top. And depending on the resistive state of this neuron MTJ, the voltage at this node will fluctuate, which will ultimately end up modulating the output current flowing from this interfaced peripheral transistor. If you were to do a device circuit co-design analysis, it is possible to show that the output current and input current variation will look something like this. By simple modification of the device structure, I can go from a non-spiking neuron to a spiking neuron. The only difference, as you see, that the pinned layer over here is at one edge of the free layer, so we are able to detect whether the domain wall reaches the opposite edge, and in case it does, we trigger an inverter to generate an outgoing spike. So a good flexibility of the design is that by very simple modification of the device structure, we are able to implement various functionalities going from synapses to neurons of different biofidelity levels. This slide shows the organization of the all-spin neural network. As you see, the domain wall MTJs are organized as synaptic devices over here. You are seeing the two peripheral transistors for reading and writing the synaptic devices, and the interfaced columns are feeding into the current that will be flowing through the heavy metal of the domain valve neurons. This is a spiking neural network design. So what are the advantages for these spintronic implementations? One of the key features, as I mentioned, is that these spintronic neurons are magnetometallic devices and require very low currents for switching. And therefore, all the supply voltages of the crossbar array can therefore be lowered down to levels of 100 millivolts because I need very low driving currents for my spintronic neurons over here. These devices are also current driven, and therefore it is possible to directly interface the current flowing from the crossbar array to the spintronic neurons. And therefore, we are able to avoid costly analog to digital converters. And it turns out that in current neural network hardware accelerators based on these crossbar architectures, these analog to digital conversions is turning out to be a significant component of the resultant energy consumption in the system. So bypassing some of these peripherals like analog to digital converters is resulting in huge benefits in terms of the resultant system level energy consumption. One interesting property also for spiking networks is that because these are non-volatile devices that are being used as neuron devices, I can avoid the costly memory transactions that I need for keeping track of my membrane potentials, which I would usually need in a spiking neural network design based only on resistive crossbar arrays. So having non-volatile neurons is helping us to avoid that memory transaction. And the reason again I would like to stress over here why we are able to utilize these devices as neurons as well as for synapses is for the unique properties of being current driven, of the input resistive path being of very low resistance so that you are able to virtually ground these vertical columns and so on. So interesting features of these devices are being utilized at the circuit and system level. Now going forward from the discussion in the previous slide, we wanted to perform a system level estimate of the efficiency of all-spin neural network designs. And before I go into that discussion, I would like to bring up a recent architectural design framework where we really explored a hybrid design where some of the layers were operating in a non-spiking mode and some of the layers were operating in the spiking mode. The motivation behind going for such a hybrid architecture was, first of all, we found that from the device implementation point of view, there is a very nice flexibility that we have in implementing different types of neuron functionalities by simple modification of device structure. On the other hand, when we were trying to design all these deep spiking neural networks, it is very clear, as you saw from one of the previous slides, because of spiking sparsity, that the peak power consumption in a spiking network is much lower than what I would have in a non-spiking ANN. But when you really go for these deep networks, because the spiking information has to really propagate along the depth of the network, the total amount of integration time, the total number of time steps that I have to wait to get reasonable accuracy seems to increase in a deep spiking neural network, which somewhat eschews the benefits that we have from the reduced power consumption, and thereby the energy efficiency benefits of SNNs get lowered somewhat than the benefits that I have for the peak power consumption. So in order to really bring down the latency disadvantage of SNNs, we explored a hybrid design where the initial layers of the network, where the peak power consumption of the ANN is very high, that was operated in the spiking mode, and the later layers of the network, which are not so much power consuming in an ANN, was really operated in the ANN mode. That helped us to reduce the time step integration process to a much lower extent, and we found that the energy consumption was reduced by a factor of around 1.5 to 3x than a pure SNN implementation. So this was a trick that we played at the algorithm level, but really leveraged some of the device advantages we had because we are able to flexibly design different neuron functionalities. Further, at the architecture side, we explored a hybrid ANN SNN architecture. So you see that the SNN cores are shown on the left, the ANN cores are shown on the right. And some of the key properties at the architecture level that we leveraged was the reduced use of the analog to digital conversion. So we used ADCs only when information had to really flow out of these neighboring tiles. So for neighboring tiles, we used current mode summation directly to drive the neuron devices, and only when we had to send out information outside of this core, we had one ADC conversion done. So it minimized the amount of peripheral ADC conversions required to be done by leveraging the current mode integration property of the spintronic devices. And as you see that, driven by all of these advantages, right? Number one, that I can reduce the crossbar supply voltages. Number two, I can get rid of some usage of the peripheral ADC conversions. And number three, by leveraging that hybrid AN/SNN mode conversion, we were able to demonstrate around 7.5x energy efficiency in comparison to ISAC, and 2 orders of magnitude improvement in respect to INXS, which was really a spiking neural network hardware accelerator design. And the huge efficiency in the spiking side really stems from the fact that our networks were really optimized for spiking networks. So far, I have not really talked about how we can implement on-chip learning. I have mainly talked about inference. So the next couple of slides, I will be discussing how to implement on-chip learning in these spiking neural networks through local unsupervised schemes like spike timing dependent plasticity. Spike timing dependent plasticity is actually based on the seminal work of Bai and Fu, who postulated that the synaptic plasticity change is very much determined by the firing times of connecting neurons, and the weight change is exponentially related to the time difference of firing between the pre-neuron and post-neuron. The key observation that we have from the graph is really neurons that fire together wire together. That is, if my delta t is positive, that is t post is greater than t pre, that is post neuron fires after the pre neuron, the synaptic weight change should be positive, otherwise it should be negative. So if the post neuron fires after the pre neuron, the hypothesis is that the neurons are temporally correlated. So I'm trying to enforce that connection even stronger. Otherwise, it is decorrelated. I'm reducing the connection strength. This slide just walks over a particular example where I have a network with 3 neurons, I1, I2, I3, driving the post neuron O1. And depending on the time of firing, as you see T1, T2, I will have a positive plasticity change, and for T3, where the pre-neuron is firing after the post-neuron, I will have a negative plasticity change. So the key features are, first of all, these kind of learning mechanisms are completely unsupervised, do not require any labeled data. And also these are local learning rules, and in stark contrast to the global learning rules that we have for backpropagation, where I need to calculate errors, gradients, backpropagate it through the entire network, etc. And especially in this era of Internet of Things with the expandable growth of wearables, some form of unsupervised learning on your edge devices is very much attractive, and you would also like that to be low power, because it is not always possible for information to be transmitted to the cloud for computing purpose as well as from privacy concerns. So these kind of learning mechanisms are really very attractive in that domain. Again, STDP should not, I believe, should not be really looked at as a learning mechanism to replace backpropagation. It is kind of an incremental adaptive learning strategy that you would like to implement for unsupervised learning on edge devices after you have already trained your network through backpropagation through some pre-training mechanisms. Now, going back to the spin synaptic devices that I talked about, how do I implement spike timing dependent plasticity in these devices? A very attractive feature of these spintronic devices is that the device conductance changes linearly with the domain wall position, and this domain wall position again changes linearly with the current, which means that I have direct proportionality between the device conductance change and the current magnitude that is flowing through my device, the programming current magnitude. And therefore, in order to implement STDP characteristics, what I essentially need to implement is an exponentially varying programming amplitude of the current with respect to the spike timing difference. And this can be very easily implemented if you think of it by interfacing these devices. MA1 to MA4 are really peripheral transistors for decoupling the write and read. If I just interface this device with a transistor which is operating in subthreshold saturation. Why subthreshold saturation? Because in subthreshold, the current that flows through a transistor exponentially varies with the gate voltage, right? So if I drive my gate voltage linearly increasing through time, and if I sample from this programming path only when my post neuron spikes, then the current that will flow through this MSTDP transistor and ultimately through the heavy metal of the device will be exponentially related to the programming gate voltage over here, and which in turn will vary according to the timing difference of the pre and post spikes. So we exclude such an array-based organization of these spintronic synapses interfaced with neurons and these peripheral programming transistors. And the key advantages again was that, first of all, during programming, you have that linear programming behavior. Linearity is very important when you want to implement on-chip learning. The programming energies are again much smaller than other emerging technologies. So that's also another key advantage for on-chip learning scenarios. And you have decoupled write and read current paths. So that is also another advantage. So in contrast to other devices, so where does spintronic devices stand in the long run? So I believe that each technology currently has its own advantage and disadvantage. For instance, RRAMs, PCRAMs are much ahead in terms of experimental demonstrations, whereas spintronic devices, we have currently started on preliminary experimental demonstrations in the research community. There have been demonstrations where people have used more than 10 devices, let's say, using such kind of devices for associative learning tasks and so on. So while the experimental side is ramping up in the spintronic domain as well, however, in RRAMs and PCRAMs, you have experimental demonstrations of, let's say, 128 cross 128 crossbars today. However, the programming energies of these RRAMs, PCRAMs devices seem to be much higher, whereas spintronic devices have much lower programming energies. They have unlimited reliability and endurance, in contrast to other technologies where variations, endurance seems to be a limiting factor. One other metric where spintronic devices do need to bridge the gap still is, for instance, the TMR ratio, or the maximum to minimum resistance ratio. Currently, although there are some experimental demonstrations that even show a ratio of around 7, ideally we would like to achieve a ratio of around 10. So that gap also needs to be bridged. There is a roadmap by the Magnetic Society that predicts that we will be very soon able to bridge that gap, but still work needs to be done in that domain. So as per my perspective, I really feel that there are interesting opportunities for each of these technologies, and it is very unclear at the moment on which technology would really be the winner in the long run. Now, probabilistic inference is at the very core of decision making in the brain. And as we are scaling down these technologies to extremely aggressively scaled dimensions, variations and stochasticity in the programming process become a predominant factor in the operation of these devices. And rather than viewing that as a disadvantage, there are a lot of research works currently that are trying to exploit this stochasticity for computing purpose. And it really becomes akin to the probabilistic inference and decision making that occurs in the biological brain as well. For instance, if I look at spintronic devices and I scale that down to monodomain magnetic tunnel junctions, because of thermal noise at room temperature, the switching probability of the device is a nonlinear function of the programming input current. And you can abstract these kind of switching probability as a function of current, for instance, as a stochastic spiking neuron. And one of the key motivations also for moving to this probabilistic domain encoding of information is that you can work with state compressed devices, in the sense that I am sort of compressing the multi-bit information that I was using previously to a binary information, a monodomain magnet, a 0 or a 1, but I'm compensating for that information loss by leveraging the switching probability over time. So this is really the key takeaway, encoding multi-bit information over time in the probabilistic switching of a single bit scaled nanomagnet. And this is exceedingly important today, because as we are scaling the devices down, we will probably not be able to get multiple states. For instance, in nanomagnets, I will not be able to stabilize multiple domains in the magnet. I will converge to a single domain. So we are anyways probably going to work with single bit devices. And as I mentioned in the initial part of the talk, then it becomes akin to having a Boolean CMOS switch. We are not gaining much, right? The only change there is that now, because of the probabilistic switching, we can encode information, therefore, in the probability domain. So we have been working in the stochastic spiking neural network domain, where the neuron devices are really these monodomain magnetic tunnel junctions with the stochastic behavior. Similar situation also for synaptic learning, where you can replace these synaptic devices by single bit devices which are highly state compressed. And we have been able to show that you can achieve ISO accuracy as a full precision network, even with a binary network, as long as you are leveraging this probabilistic switching over time. So that's really the main advantage, state compressed networks. There is also a good amount of work in the field on going to very aggressively scaled devices in the super paramagnetic regime, where the magnet spontaneously starts flipping between the two extreme states, and this is referred to as telegraphic switching very low barrier height magnets. That is, it is kind of becoming a volatile device at this point, and the behavior kind of remains the same. On the left hand side, you see the behavior of a high barrier height magnet. This is a conceptual device that does not read out the magnetic state through this magnetic tunnel junction barrier, but uses a phenomena which is called anomalous Hall bar. Kind of the same material stack that I'm showing you here, heavy metal and a ferromagnet lying on top, but you're really reading out the magnet state to these V plus and V minus terminals. You're passing current through these I plus and I minus terminals. If I were to tap out the switching probability, I will get that nice sigmoid looking curve that I showed previously. When I move over to a telegraphic switching regime, the same thing really happens. By passing a current in the appropriate direction, I'm able to modulate whether the device will stay in the anti-parallel state or the parallel state. And if you integrate the information, you get the same kind of sigmoid behavior, that is average output voltage as a function of right current. The instantaneous behavior kind of looks like this telegraphic switching characteristics. Why would I want low barrier height magnets? Because of very fast operation of the circuit. Because these are highly scaled devices, the operating power consumption is much lower, it is much faster. However, there are also some circuit level concerns, like the device becomes extremely sensitive to the read noise. And because this becomes a volatile device, I need to continuously write and read the states, because of which the write and read paths are always active. And therefore, the read circuit needs to be highly optimized in this scenario. Nonetheless, there has been a lot of interest in super paramagnetic devices, and mainly because of that fast behavior, the fast operation of the MTJs, and really because of the telegraphic behavior of these devices, you can operate this in the asynchronous mode. In the sense, I do not need to wait for a sequential time state based operation that I do for high barrier height magnets. I can just let the magnets operate over time in the telegraphic switching regime spontaneously. And if I average out the outputs in the long run, I will get to those sigmoid-like probabilistic switching curves. Now, one disadvantage of these kind of super paramagnetic tunnel junctions is that these parallel and anti-parallel device lifetimes, both of them get modulated really depending on the magnitude of the incoming write current. What really I am changing is, if you remember, the output was the average output voltage. That varies in a non-linear sigmoid fashion as a function of the input current, but we do not have precise control of the device lifetimes. So in one of our recent proposals, we explored a magnetic tunnel junction stack where we had a magnetoelectric layer at the bottom. And because of ME coupling between the free layer and the magnetoelectric layer, what we really achieved was independent control of the device lifetimes. That is, one of the voltages applied to the top of the magnetic tunnel junction stack was able to control one of the device lifetimes, and the other voltage applied across the ME layer mimicked the application of a magnetic field, sort of. And if I were to look at this energy profile of the magnetic tunnel junction, it really gives you two independent control knobs to modulate the device lifetimes independently. And we were able to achieve that very nicely in our devices. As you see, the y-axis is one of the voltages, the x-axis is the other voltage. And I'm plotting the tau p and tau ap, and as you see that these nice vertical and horizontal contour lines essentially indicate that the device lifetimes are kind of independent of one of the voltages and dependent on the other voltage. So what is the advantage for having this kind of independent control of device lifetime? The advantage comes from the perspective that so far a large section of spiking neural network algorithms are really utilizing rate encoding. That is, I'm observing the behavior of the network over a long period of time, which contributes to its inference latency as well, one of the disadvantages for SNNs. However, there is a growing body of work in the SNN community on temporal information encoding, where I encode the information in the precise timing of spikes. Let's say the time to fire of the neurons in a particular network, and then the winning neuron can be the neuron which fires the first. In these type of temporal encoding, because you are modulating information based on precise timing of spikes, these are much sparser, these are much faster also to infer. So many of the disadvantages of SNNs goes away in the temporal information encoding scenario. These kind of devices where you are able to precisely modulate the temporal behavior of the neurons will be imperative to realize temporal spike encoding in such networks. So this is kind of one of the futuristic devices that we are looking at, where you can potentially implicitly encode timing information in the device itself. Now, as I mentioned before, spiking neural networks have some unique properties like temporal behavior and sparsity of information that is propagated between layers of neurons. So it is very much suited for application drivers that also naturally have these properties, and they are a direct fit to such application drivers. One very popular application driver that people look at in the SNN community are event sensors. This slide is actually showing a snapshot from the Prophecy website, which is actually a company that manufactures such event-driven sensors. It is inspired by biological sensors, the way it operates, and the key advantage is that these sensors only transmit information or only acquire information only when the light intensity changes. So it is very good for tracking tasks. For instance, if you see a conventional sensor, it is frame based, it acquires all the incoming pixel intensities in a particular frame, whereas event based sensors send in asynchronous spike stream only corresponding to pixel locations that change over time. So it is much lower power, the dynamic range is very high, and it is very fast. So these kind of sensors are very promising for spiking neural networks because it naturally fits with the asynchronous event-driven computing scheme. There is a lot of interest right now in event-driven sensors, and in one of our works, we recently explored DVS gesture recognition, the dynamic vision sensor gesture recognition, and we achieved state-of-the-art recognition accuracies with very low integration times, whereas most of the other approaches usually require a much larger duration of time for inference purpose. One other application area that we have been exploring is smart grids. Disturbance classification in smart grids is a very challenging problem today, and real-time online classification even more so. However, unique properties that we have in smart grids is that the probability of occurrence of a fault is really sparse spatially and temporally. Spatially, because whenever a fault occurs in one particular geographical location, you will probably have clusters around that point. So spatially and temporally, both things are sparse, and it's also temporal. So again, this is a very natural fit to SNN computing framework, and we recently showed that by leveraging this property in SNNs, you are able to get to around 83% energy savings on a large-scale smart grid system, which is kind of a benchmark in that field. Now, going forward, I would like to conclude with a brief outlook of my perspective of things that we can look at in the neuromorphic computing area, going beyond the current focus that we have in this field. On one side, I feel we need to take a bottom-up approach, that is, investigate other aspects of the brain, other computational units of the brain that contribute to cognition beyond neuron and synapse. One particular area that we have been focusing on are astrocytes or microglia. It turns out that these kind of cells constitute a significant portion of the components that we have in the brain. Even some studies have reported more than 50%. However, these functionalities have really not been imbibed so far in the neuromorphic computing field to the extent at which we see for neuron and synapse functionalities. Astrocytes perform a multitude of functions ranging from learning, temporal information binding, and so on. One aspect that we have been focusing on over the past year or so is self-repair. Astrocytes contribute significantly to self-repair in the brain. As you see over here, there is a particular network where there is a fault occurring in one of the neuron synapses. This connection is faulty, and it turns out that by retrograde feedback signaling from other neurons in the network, an astrocyte, which is kind of mediating information across multiple neurons, they are able to initiate self-repair by this indirect feedback signal by increasing the transmission probability of the healthy synapses. So for instance, over here, if I look at this graph, right, whenever there is a fault that occurs in one of the synapses, and you can see over here N1 is the blue neuron and the orange one is N2. Fault is occurring at this time step, 200 seconds, right? And therefore, the orange firing frequency instantaneously drops to a very low value because of the fault. You can see that this is at 0. This is the transmission probability that we have. Now, the healthy synapse, which is the green one for N2, the orange one is the faulty synapse for N2, that is 0. The green one, though, increases its transmission probability, and that ends up happening because of a feedback signal from the other neurons. And we were able to show that in STDP based unsupervised learning networks that I showed previously, if I were to have faults in the synaptic connections, I'm able to recover the accuracy of the network by including astrocytic functionality based self repair. And we were able to show around 9% accuracy improvement on MNIST, about 5% accuracy improvement in FMNIST datasets with 90% faults. So a significant degree of self-repair can be achieved in these networks, and this can potentially enable neuromorphic platforms which are capable of autonomous self-repair. Coupled with this perspective, I also feel there's also the need to go for a top-down approach where we explore network architectures that are different from the current convolutional network architectures that we sort of use in all scenarios. For instance, in the brain, it turns out bottom-up and top-down information processing both take place. But in standard deep networks, we only consider bottom-up projections. Top-down projections are usually absent. One area we have been focusing on in that perspective is Bayesian deep learning, where the network weights are trained in such a manner that you envision those as probability distributions, and the posterior distribution of the weights are really learned based on the incoming information that I have. These kind of Bayesian deep learning is very popular for getting some amount of uncertainty quantification from the network, and this is very attractive for application domains like autonomous driving, where you would like to have some form of uncertainty quantification from the network. So trying to have an estimate of explainability in the machine learning algorithm is very much important today, and we believe such networks will have an important role to play in the long run from a machine learning perspective. Now, how do we accelerate these kind of applications from a hardware side? Again, because you are really trying to implement these networks by modeling the weights as probability distributions, you can leverage some of the noise that we observe in these devices from a computing perspective instead of viewing it as a disadvantage. So for instance, if you remember, I have talked about that the spintronic devices can be used as a random number generator, right? Now, if I were to draw some insights from central limit theorem, central limit theorem tells me that if I were to have a sample of these random number generators and I were to have a new random variable that is the sum of all these random number generators, with increasing number of these random number generators, I would be able to closely mimic a Gaussian probability distribution. So one of our recent works really drew insights from central limit theorem to implement a neural network where we have probability distributions for each of these synaptic weights, and we are really implementing those by drawing such insights from probability statistics and leveraging device level non-idealities like thermal noise. So to really conclude the talk, neuromorphic computing is an interesting field that really lies at the intersection of materials, applied physics, circuit design, architecture design, novel sensor design, neuroscience concepts, machine learning. So it is a very interdisciplinary field trying to get insights from all of these stacks. And through this end-to-end core design of all these perspectives, we would be able to reap the benefits of event-driven sensing, hardware design, and application drivers and algorithm development. So hopefully you have now a perspective of the key innovations in each of these fields that one can target, and how the end-to-end core design can potentially enable us to achieve a quantum leap in the efficiency of AI systems. Thank you so much, and I would be happy to answer any questions.
Okay, so I'm happy to answer any questions anyone has.
Sir,
Yes.
sir, as the is the mix as this language discipline is the mixture of the some electronics field, some computer science. The computer science student, if goes in this discipline, is they can easily understand that what has happened.
I mean, of course, you need to have some background. There is a good amount of background needed from computer science, deep learning, algorithms, etc. You have to take some courses and so on. But yes, some background on the CS side is also needed.
I mean to say that as the circuit design is fully an analogical part,
Mhm.
then it is
Yes,
possible
so
to
there is
go,
some
go.
interdisciplinary work. So you can of course pursue research primarily on the algorithm side, but if you are interested in the hardware side as well, that is also an option. I guess the best part is the mix of the two fields.
No, you may only go for the algorithm part. It is possible in here. Only
Yes,
go
yes,
for the algorithm part.
that is also possible. Yes,
Thank you, sir, for this clarification.
thanks.
Sir, uh, do you think that this area can be more expanded by further research from our historical traditions? Like some scientists have developed the Panini machine and have also included several technologies from ancient Indian nanotechnology. Is it possible?
That I'm not sure. That might be an interesting question, but yeah, I'm not very sure about that part though.
Okay, sir. Thank you. Nice presentation, sir.
Thanks.
Hi, Abronil. Just a question. From the application side, is there any possibility or how you look into maybe next 5 years or next 10 years? Is there any DLML, this model will come to, say, BFSI or say banking? How you can look into? What is your
Right.
comments
So
or
I
what is
think,
your take?
yeah, so I think we are mainly looking at applications where you want to deploy. So if you're looking at standard deep learning, yes, I mean, all types of applications people are looking at, like banking, in the financial sector, or natural language processing, and so on. Specifically for neuromorphic computing, though, we are looking at applications where you're deploying these ML systems in resource constrained environments, like mobile phones, or let's say in defense applications where you will need to operate robots and autonomous agents in power constrained environments. So that is where I think the application domain for specifically neuromorphic computing lies.
Okay, thanks.
Anybody would like to ask any questions? The floor is open. Participants, you can ask questions if you want. Any questions from any participants? Okay, fine. Abril, I have a question. Yes,
Hello.
please carry on. Please
Yeah.
carry on.
Yeah. I'm Saurabh Samanto from Bardhaman University. Yeah. Sir, I
Please
have
go
one
on.
question. Yeah. Sir, I have one question. What is the software available for the spiking neural network? Basically, I would like to say if I want to focus on the only the training part and to solve the different kind of problem like classification problem or any other kind of problem, then what will be the suitable software?
Right. So I think there are multiple options available. I guess if you are using PyTorch, TensorFlow, there are already libraries available for spiking networks. But you can really use many other options like MATLAB, etc. So
MATLAB is
really,
in the MATLAB environment is available.
yes. I mean, it is more or less a modification of standard deep learning codes. So if you want
Okay.
to do in MATLAB, that is also doable. Yeah.
Actually, I would, generally I use the MATLAB environment. That's why I am asking.
I see.
Okay.
Yes,
Okay.
that is good.
Okay. Thank you, sir.
Anybody else? Okay, Obrunil, I think I have a question to ask you. The question is that currently in US, what kind of research is going on in the neuromorphic front? Absolutely, I want to know the latest news.
Mhm. So I think the research is going on more or less at various frontiers. One being, for instance, looking at novel hardware where you can map various biological functionalities to the intrinsic physics of the devices. There's also a huge amount of work to draw inspiration from theoretical neuroscience and how we can modify standard machine learning algorithms to be more brain like, which has kind of strayed more towards the mathematics and statistics side currently. Then you have also a huge amount of work from the algorithm side where people are trying to design um, spiking neural networks to surpass standard deep learning algorithms, since these are very new systems and therefore a huge amount of research investment is also being done on that front. So I would say more from the neuroscience, algorithm, and hardware side, all three angles.
Okay. So I think what I was trying to understand that Penn University is in the forefront as I understand. But what about the other universities or industry as such?
Right. So other universities, there are other universities where neuromorphic computing research is going on in US as well as abroad. Like in Europe, there's a huge amount of work going on there as well. Industry-wise, I think Intel, IBM have invested. Intel already has a huge amount of investment in terms of neuromorphic chips called DOIHI that they are trying to push forward. There are many startups like BrainChip and so on who are also proceeding with neuromorphic processors. So I think both from academia and industry, there is a huge amount of interest in this field.
Okay. Abronil, there are many questions that are coming up to my mind, but I understand your time is very precious. And one thing that I know this is basically a mind boggling presentation for the last 90 minutes, 1 hour 30 minutes. I was watching this presentation. It's really mind boggling. And the kind of research that is being carried out in your institute as well as in US, I'm sure, unbelievable. Do you think that in India, we are having a similar kind of infrastructure to carry out this kind of research work, or is any research work is going on in India, which your university is jointly doing?
That's a good question. So I think definitely there is research being pursued in this area in India. I know of fellow colleagues at IIT Delhi, IIT Bombay, ISC Bangalore who are working in this area definitely. And yeah, I think ongoing collaborations are definitely present. Yes.
Okay, okay. Participants, if you have any questions, this is an opportunity because Dr. Shengupta is primarily a researcher. He is not only a professor, but he's also a researcher. He has the experience of working in Intel labs. So I think if you have to clear any doubts in your mind, this is an opportunity. This is a platform where you can exchange your ideas, or you have any queries, you can just raise those queries.
Sir,
Please.
sir, is there any application in the field of the new biological neurobiology?
Right. So I think there is also a good amount of research being invested, especially in Europe. They have a project which is called the Human Brain Project, where the idea is really to mimic brain-like functionalities in hardware to understand how the brain works, so that we are able to decode various brain diseases like Alzheimer's, Parkinson's, and so on. So I think that is a huge push in Europe that is present, and I think US is more focused on the application side in terms of defense applications or computing applications in general. But to answer your doubt, yes, there is a huge implication on understanding brain functionalities as well when it comes to new neuromorphic computing.
But I mean that using neuromorphic computing, it is easily to understand by near future that how the brain works and how disease of the various brains. I mean, in the
Yes, that is correct.
psychological disease is happen and how to overcome this disease in the near future from this field. Am I right or wrong?
Yes, that is correct. Yes.
Thank you, sir.
Any more questions?
Sorry, I have a question. My name is Ruthi Somadar. I am life member of CSI, but I am not in India. I am connected from another part of the world. Question is not to Avronil. Question is to, or request rather, to Saurabh Chakraborty. Can you share this PPTs what he has shown? It's a very
Actually,
eye opener. So
in fact, you are correctly pointed out that. In fact, in the opening speech, I have said that this is the first time from CSI platform we have organized this kind of
yes, yes,
program. And I don't know whether in the country this kind of program has been held. And I have been
right,
talking to Abronil for the last 1.5 months on this particular program, because these programs cannot be organized overnight, as you understand. Because
correct.
Abronil is, as I have mentioned, that he's a very busy researcher and he travels quite a lot. So the problem is this: yes, I will have a talk with Dr. Sengupta, and I will try and see how best we can explore this opportunity, the one which you have talked
Sure,
about. And if in case something is coming up, I will definitely be in touch with you. Just drop in your email ID and I will get back to you on this. Okay. And
sure.
okay.
I am
And
also in a different time zone for your information when it is just early morning. So I just
where
get
are
up
you?
because of this. It is a different country in Africa.
Oh,
Okay,
Africa.
so
Oh, great.
so it is a 5.5 hours difference. So I just
Okay.
because of this subject and interested because what is happening into the field of neurotechnology,
Morphic computing.
basically basically is brain. So how we
Absolutely.
are copying that, how we do that is a really good, interesting thing. And CSI, thanks to you.
Thank
Okay,
you very
if it
much,
is
sir. Thanks a
shareable
lot.
and it would be helpful for. Okay.
Absolutely. But don't forget to send me an email. Do you know my email ID?
I will send that email which I got it from CSI. Okay,
Okay, you
I'll
just send
reply
it
to
to,
that.
yeah, just write to the chairman, CSI Kolkata chapter. That's all. And I
Okay,
will get the
okay,
message and I will just take it up from there itself. Okay.
okay. Thanks a lot.
Okay. Okay. But one thing, probably the question that you have raised, I'm just pondering whether I can ask this question to Dr. Sengupta. Can we organize a program which is more similar to it, but not exactly the one which we have discussed today, either from your institution or from any other professor from some other institutions who can talk on this? That will be of great help. I'm sure the entire society, the Computer Society of India, will definitely benefit from this. Abdul, your views, please.
If you allow me, maybe I can just request him that maybe we will have a follow up. Okay, maybe some interesting thing, pattern recognition or face recognition, those kind of things. It can be included into that. I think it will be more interesting. I don't know. I'm just telling from my side.
Okay. Abdul, your views.
Yeah, I think we can think about that. I have to think of what to present, etc. And I guess we can discuss that offline and see what we can do.
Okay, okay, that's fine. That's fine. Absolutely okay. No problem. No problem. Anybody else who like to raise any question?
Sir, I
Uh,
have a question.
Yes, quickly, tell me.
Sir, how long until we'll see all this technology outside in the real world?
That is a difficult question. I think minimum 10 years, I guess.
No, but probably I think what he was trying
I think
to.
no. I think to answer that question, I'll request that guy to log into Metaverse. We will get some kind of sense out of that what he's talking about.
And in fact, as I have
Okay.
mentioned at the beginning, to all for the benefit of all the participants, as I have mentioned in the beginning, please visit the lab, neuromorphic lab, which is maintained and who is the custodian. The main custodian of this neuromorphic lab at Penn State University is Dr. Abrunel Sengupta. So please go through that lab. You will learn quite a lot. I am telling you. Just go through it once. Okay, and those who are particularly interested to work in the field of neuromorphic computing, I think they must visit that particular site. It is there also in the flyer that has gone to you, that has been circulated. This website reference is there. So if you are interested, just click on that and you just get the details, whatever details you want. I'm sure you will be quite enriched with your knowledge. Any other questions?
Hello, sir. Myself, Rupashri Chaudhuri. I am a final year student of MTech of Bajbaj Institute of Technology.
Please go
Uh,
ahead.
Sir, I want that if you give us your presentation by email, that it will be help for us.
No, that we have discussed just few minutes back. We need to have a talk with Dr. Sengupta, and then once it is finalized, probably then we will be in a position to share that with you. But we have not talked on this. The request has come few minutes back. In case it is being worked out, we will definitely share with you. I will keep a note of Ruposri. No, don't worry.
Okay, sir. I in the mail we received that you send us a certificate from your side, so you can attach that.
I
Uh,
have a request to all the participants who are present here. My dear friends, please, I have already sent a message that those who have attended this program in full, which is mentioned in the email, in the body of the
yes,
email
yes, sir.
itself, that
Yes.
you will get a certificate. The only task that you have to comply with, just send a one liner email. Don't send lot of lines, don't write too much. Just send one line email stating that I have participated in this program in full. Kindly issue a certificate. That's all. That's period, and you will get your
Okay, sir.
certificate.
Okay,
Okay,
sir. Thank
so
you. Thank
it
you.
is
Thank you, sir.
applicable. It is applicable for all the participants, those who are present today. Everybody will get. It's not that you.
Ye-
It is only you who will get.
So,
Everybody will get.
could you please repeat what
Okay, sir.
mail we have to write?
CSICal@gmail.com. The same mail from where you have
Okay,
got
sir.
your. It is the same email ID.
Okay, sir.
Okay,
Thank you,
sir.
sir.
Thank you.
CSICal@gmail.com. It is very simple. CSI
Thank you, sir.
Cal is CALCal@gmail.com. May
Sir,
I,
here is
Arup,
hello, sir.
just a minute.
Sir, here it is
Arup,
written that csical.drive1@gmail.com. Is
yes,
it?
that is the second one. Both are correct. Both are correct, sir. Both are correct. You can do that.
Okay, sir. Thank you, sir.
That is not a problem. Sharup, we have a backend team which is still in the office. It is very late in the night, but you must appreciate the kind of pressures these people they take. All my three office staffs are there currently working in the CSI office. I will request Sharup to kindly just send a small message, just one liner here itself, about the two email IDs. That's all. Okay, don't write anything else. Just mention the two email IDs. Okay, somebody was talking, sir. Any question? Somebody was raising any question. Anybody?
Sir,
Uh, Please go ahead.
sir, which email ID I sent? Oh,
Oh,
this.
yes, you must have got that. It is in the screen. You can see that.
Yeah, one email ID is.
Yes, you send that. You send all your requests to that particular email ID only. That will be better instead of sending to You can send that, but instead of sending in multiple email IDs, you can send this to one email ID, that is csikal@gmail.com. It is easier to remember. It is easier to write also. Okay.
Sir, what will be the body of the email?
Just one liner, madam. Kindly issue a certificate. I have attended the program in full. That's all. We have a database, when we organize this kind of programs, we have a database which is maintained at the back end. So whoever is joining this program, his joining time, his leaving time, everything is mentioned there. Okay. So you don't worry. The backend team is quite strong and they will take care of everything. If you have attended the program in full, you will get a certificate. But my only request is this: they are also doing a lot of work in the office other than this webinar. So my request to you will be just send a one-liner stating that I have attended this program. Kindly issue me a certificate. The balance they will do. They will check the database. They will check your in time. They will check your out time, and they will issue the certificate. Okay. Any other question? If we don't have any other question, then I will formally close this session. Before I close this session, let me tell you one thing, that CSI is in this financial year, CSI has organized, if I'm not wrong, at least 10 webinars. All are excellent webinars, but I think the one which we have attended today, it has reached a very, very uh, fantastic level. Not only that, the standard of presentation, you see, this is very, very important, and you see the quality of presentation that we have seen today, it's mind boggling. So my sincere thanks to Dr. Abronil Sengupta for sparing his time, for giving such a wonderful presentation. And I'm sure you have done the question answer session. You have handled the question answer session very, very nicely. And I'm looking forward for more such sessions with you. And because there will be a lot of requests that will be coming to me, I'm sure. In fact, I'm getting phone calls also. While this session was on, I was getting so many phone calls whether we can organize this program again. So I said, let me work out on this and I will get back to you on this. So, Abdul, once again, many, many thanks to you. My request to you only will be that, as you have rightly mentioned, that you can offline, we can definitely talk and we can see how best we can take this initiative forward. Abdul, I think it is now quite late at Calcutta. It's around 9:30 in the night. So,
Yes, thank you so much also for the invitation, and it was very nice talking to all of you. I
my
enjoyed also
pleasure.
the presentation and mine.
My pleasure, Abdunil. My
Thank you,
pleasure,
sir.
my pleasure. Thank
Sir,
you
thank you,
very
sir.
much, Abdunil.
Thank
Thank you, thanks a lot. Thank you
you.
very much, thanks a lot. Abdunil, thanks a lot once again. Look forward.
Thank you to all of you. Yeah, thank you.
Thanks a lot. And we will be in touch, okay? We
Yeah,
will be in touch. Okay.
take care.
Thank you. So I declare the program as officially closed. The backend team, they can wrap up and they can proceed, okay?